Today, I will explain how eSIM profiles are loaded onto a device by a mobile network operator and what information is actually stored inside the secure element of the eSIM. First, let us briefly understand what an eSIM is. An eSIM, also called an embedded SIM, is a programmable SIM chip that is permanently built into the device. Unlike a traditional SIM card, it cannot be removed. Instead of inserting a physical SIM, the mobile operator remotely installs a SIM profile onto the device. This remote provisioning system is standardized by the GSMA and defined in specifications such as GSMA SGP Part 22. The key component inside the device is called the EUICC, which stands for Embedded Universal Integrated Circuit Card. This chip acts as a secure element, similar to the chip inside a physical SIM card. Main components in the eSIM ecosystem. To understand the process, we need to know the main components involved in the eSIM ecosystem. The first component is the EUICC, which is the secure hardware chip inside the device that stores SIM profiles. The second component is the Local Profile Assistant, or LPA. This is software running on the phone that manages profile downloads and activation. The third component is the SMDP Plus server, which stands for Subscription Manager Data Preparation. This server stores the operator's encrypted SIM profiles and delivers them securely to devices. Another component is the SMDS, or Subscription Manager Discovery Server, which helps devices locate available profiles. Finally, there is the Mobile Network Operator backend, where subscriber credentials and SIM data are generated. Step 1. User receives an activation code. The process begins when the operator provides the user with an activation code. In many cases, this is delivered as a QR code. The activation code usually contains 3 pieces of information: the protocol version, the address of the SMDP Plus server, and a unique activation code. When the user scans the QR code, the phone's local profile assistant reads this information and prepares to download the profile. Step 2. Device contacts the SMDP Plus server. Next, the local profile assistant establishes a secure HTTPS connection to the SMDP Plus server. At this stage, the device identifies itself and requests the SIM profile associated with the activation code. The communication between the device and the server is strongly secured because SIM credentials are extremely sensitive. Step 3. Authentication of the EUICC. Before the profile can be delivered, the EUICC must authenticate itself. Each eSIM chip contains manufacturer certificates and cryptographic keys installed during production. These certificates are part of a trust chain managed by the GSMA. During the connection process, the EUICC performs mutual authentication with the SMDP Plus server using secure certificates. A critical security rule is that private keys never leave the secure element. Even the phone's operating system cannot access them. This ensures that only the legitimate eSIM chip can receive and decrypt the profile. Step 4. Download of the encrypted profile. Once authentication succeeds, the SMDP Plus server sends the encrypted SIM profile package to the device. The profile is encrypted specifically for that individual EUICC chip. Even if someone intercepted the download, the data would be useless because only the target EUICC can decrypt it. The local profile assistant simply acts as a transport layer. It forwards the encrypted package to the EUICC for installation. Step 5. Profile installation in the secure element. The EUICC then installs the profile into its internal secure file system. At this point, the profile exists inside the chip, but is not yet active. Modern eSIM chips can store multiple profiles from different operators. Each profile is isolated from the others for security reasons. Step 6. Profile activation. Finally, the user selects the profile to activate. The local profile assistant sends a command to the EUICC to enable that profile. Once activated, the profile behaves exactly like a traditional SIM card. The phone can now register on the mobile network using the credentials stored in the profile. Typically, only one profile can be active at a time, although several profiles may be stored. What is stored inside the eSIM secure element? Now let us examine what information is actually stored in an eSIM profile. In reality, a profile is almost identical to the file system of a physical SIM card. Its structure follows standards such as 3GPP TES 31.102. The first important element is the IMSI, or International Mobile Subscriber Identity. This number uniquely identifies the subscriber in the mobile network. Another critical element is the authentication key, known as KI. This secret key is used during network authentication procedures, such as the AKA authentication protocol. The key is never exposed outside the secure element. The profile also contains network configuration parameters. These include preferred networks, the home public land mobile network, and lists of forbidden networks. Another important part is the OTA security keys. These keys are used for secure SIM updates over the air. The OTA mechanism follows specifications such as 3GPP-TS 23.048. Using these keys, the operator can remotely update SIM files or install new configurations. The profile also includes SIM applications. Common examples are the USIM application, which handles LTE and 5G authentication, and the ISIM application, which supports IMS services such as VoLTE. In addition, the profile contains various network access files used for mobility management and location tracking. Internal structure of eSIM profiles. Inside the EUICC, profiles are organized in a secure storage structure. For example, the chip may contain Profile 1 from operator A, Profile 2 from operator B, and perhaps additional profiles that are currently disabled. Each profile has its own file system, authentication keys, and SIM applications. Profiles can be enabled, disabled, or deleted without affecting the others. Security model. Security is one of the most important aspects of the eSIM architecture. Profiles are encrypted specifically for a single EUICC chip. Sensitive keys never leave the secure hardware. Even the device operating system cannot read them. This ensures that subscriber identity and authentication credentials remain protected. Final important observation. From the perspective of the mobile network, an eSIM is essentially indistinguishable from a physical SIM card. The network only sees the standard identifiers, such as the IMSI, the authentication responses, and the device IMEI. All the complexity of remote provisioning happens outside the core mobile network. In summary, eSIM technology replaces physical SIM cards with remotely downloadable profiles stored securely inside an embedded chip. The provisioning process involves secure authentication, encrypted profile delivery, and installation inside the EUICC secure element. Once activated, the eSIM behaves exactly like a traditional SIM while providing the flexibility of remote provisioning and multiple operator profiles. Thank you.